So my name is Kathleen Morse. I'm the founder of Advanced Materials Applications, and I'm the case's sponsored principal investigator in the Gumstix evaluation in low Earth orbit. My team includes software engineer Jeremy Zawadny, John Sampson from Honeywell, and also AstroDev. So we've been talking a lot this week about using terrestrial computing power in space. It's clear that there's a need for this. If you look at the computers on the right here, the upper right computer, Proton 200K, is about 10 centimeters by 16 centimeters. The price that I was quoted is $120,000 for one unit. It's a digital signal processing board. Below that is a terrestrial-based processing board. It's the Gumstix Computer on Module technology. It's about the size of a gumstick, and in contrast, it costs about $100 to $200 per unit. In addition to having the digital signal processing capability, it also has graphics processing along with a general purpose processor. So space-qualified computers, as a lot of you know, the rad-hard computers typically are a few generations behind the terrestrial processing technologies. They do tend to be 2,000 to 5,000 times more expensive, and they're significantly larger in size, weight, and power consumption. So for the goals of the CubeSat missions, obviously there needs to be a balance with high rel parts and potentially integrating in COTS. There is, as you all know, very much a need for space-based computers to support very computationally demanding tasks. These include signal processing and analysis, data capture, sensing and detection, and there has been some discussion of autonomy. So with a lot of onboard processing capability, you can basically operate without a ground station. So we were interested in evaluating the Gumstix technology, and I should also mention we're evaluating other microcontrollers and system-on-chip technologies also for space, but this program is primarily focusing on Gumstix at the moment. The Gumstix are small in form factors. I mentioned they're Gumstix size. They weigh a few grams. They're very low in power consumption. When it's running a workload, it's basically a peak power of about 2 watts. But actually, we just uploaded a new operating system on it that actually brought down that peak power substantially. So I don't have the most recent number, but it is now below 2 watts at full when it's completely maxed out. It does use most current generation OMAP processors with ARM Cortex-A8 architecture. It has been used in a lot of industrial applications, including many supercomputers. Sandia National Labs created a supercomputer that's about the size of a medium-sized suitcase, containing about 200 nodes. In addition, they've been used in robotics and unmanned air vehicles, and they are being investigated in the dependable multiprocessor product by Honeywell. In the upper right image here shows a chassis that carries 8 of these Gumstix. So you can understand why there's an interest in this kind of technology. And our study is really the first study doing both a ground-based radiation study and a space-based LEO study of their performance. And this is an important step towards the use generally of COTS. I'm going to discuss a little bit more about some of the details of the testing we've done and the results. So that'll be in the next few slides. So in September 2014, we will have these Gumstix outside the International Space Station on the external module. It's shown in this, it's kind of a blown up image on the left here. But basically, the key questions we'll want to answer is how will they perform in a low Earth space environment? This environment in LEO has a lot of heavy or high energy protons that basically can range from 10 MeV up to 200 MeV. There's a lot of heavy ions, and basically these are both known to cause single event effects, both of latch-up and single event upsets, along with single event functional interrupts. The other key question we want to answer is what is the net operation time for each of these modules while in space? Every time we detect either a single event functional interrupt that basically stops the processor, or we detect a high current event, we're going to have a hard reboot to the system. And so the idea is if these events occur frequently, we're not going to get much operation time, so that would also degrade their value in space. And then finally, we want to know if the module performance will be affected by the feature size of the CMOS technology. We're going to be flying 3 different models of Gumstix, one's 65 nanometer feature size, another's 45 nanometer feature size. And typically, the smaller the feature size, the more frequent your single event effects are. So that's another question we want to answer. I'm going to spend a little time on this slide and discuss this in some detail. We have done some radiation testing so far. When we look at the space environment, typically, as been discussed in this meeting, we look at total ionizing dose, which is the integration of all the radiation your part sees over the life of the mission. In our low Earth orbit mission, it's less than 6 months, or it's around 6 months direct exposure to space, and we're talking about less than 0.1 kilorad. So it's not a very aggressive environment, but we are periodically going through the South Atlantic anomaly, so that does tend to be a fairly aggressive environment. The other thing we look at, of course, are protons, because near Earth orbit you have a lot of protons, various energies, and as I mentioned, the proton energy, usually any energy above 10 MeV to 200 MeV can cause substantial, basically single event effects. So the thing that's not mentioned here is the middle ground between total ionizing dose effects and protons, which cause single event effects. And this is called microdosing effects. And in the future, these presentations, I'll include a slide on this. But basically, this is the middle ground where you can have one proton that can actually degrade the performance of a part. And what we've seen early in radiation testing, or indicated in early radiation testing, is microdosing occurring from one proton event that basically can cause stuck bits in the RAM, the SDRAM of the Gumstix. We're doing a second set of tests just to confirm that this is a real effect. We'll be doing those in late January. So this is our space payload. We have about a volume about 30 centimeters by 10 by 10 centimeters. As I'm highlighting here by this red dot, you can see where it's going to be located on the external module. The racks on the side actually are not going to be there, so it's just that one rack in the middle. And the Gumstix are actually going to be pointing in the anti-velocity direction. So as the ISS is moving, it's pointing opposite the direction of motion. And it's going to be an unshielded exposure to space. And so what you can see here is we're going to be testing 4 different Gumstix, and they're going to all be connected to a radiation tolerant, or what we think to be a radiation tolerant watchdog. In addition, we hope to fly some other technology in this volume in the middle to do some other radiation testing on other technology of interest. We're working with NanoRacks to do the payload integration. And basically, this unit is going to integrate with the power and communication system of the ISS. So we're going to have a semi-real-time downlink to the ISS, so we can actually watch the performance of the occurrence of single event effects. So in the space experiment, we're going to be testing 3 different models of Gumstix. They're going to be the sandstorm, the earth, and the water. So in flight testing, we're going to be basically testing the CPU and the RAM, and we're going to be running workloads constantly. And when single event upsets, or I should say miscalculations, are basically detected, we will record these as a single event upset. In addition to the RAM and the general purpose processor, we'll also be evaluating the onboard NAND flash. In ground-based testing, this is where we do the baseline or high functional test. We look at CPU stability before and after testing. We look at the performance of the RAM. Is it going to pass the memory tests? And then we do the same for the NAND flash, and we do some evaluation of other peripherals in addition to the graphics processor. So as I mentioned, we're going to have a radiation tolerant watchdog, and what that's going to do is when it detects a high current event, it will basically do a hard power cycle on the Gumstick and record the event. And then basically, as the mission continues, as I mentioned, there's going to be a detection and recording of single event upsets and single event functional interrupts that could affect the heartbeat being received from the CPU over to the watchdog. So as I mentioned, the program started in April this year. We did do proton testing at Crocker Nuclear Facilities at 64 MeV. We're doing a second proton test in Massachusetts. We're going to be testing it at 64 MeV again and also at 200 MeV. And the big thing we need to be watching out for is basically this microdosing effect, because most people do talk about total ionizing dose. They talk about single event effects, but they don't talk about this one effect that does show up a lot in especially SD-RAM. So I did want to emphasize the fact that you can have multiple computers, and certainly there can be a miscalculation, and you guard against that by voting. But if your parts are degrading over time, just because of a minimal exposure to protons, basically it can have a bad outcome for the mission. So after this next radiation test, we're going to deliver it to NanoRacks in March. And then in September of this coming year, it'll be launched, and it'll arrive on the outside of the International Space Station. It'll be exposed to low Earth orbit for about 6 months. And then I'll return about early 2015. And the interesting thing about this test is you have ground-based testing where you're doing testing rapidly. And then you have space-based testing, where you're looking at the actual environment of space. I think there's a lot of value in down-selecting parts based on, careful radiation testing, even if it's just kind of like ballparking what the performance is going to be. Because I think before you invest a lot of time into putting these missions into space, it's kind of a good idea to know where things are going to fail. And as I mentioned, I'm seeing right now in my early radiation studies that really all COTS is not suitable for space. So it's just good to do some baseline checking before you start putting technology up there. You might ask the question, why are we putting Gumstix in space? But I do think it's also valuable to compare. We're doing aggressive proton testing on the ground. We are going to get pure protons in LEO. So the question is, where's that middle ground? But if anybody had a question regarding, what was the total ionizing dose when I started seeing memory failures, we're talking about 0.1 kilorad to 0.3 kilorad. So this is pretty low radiation amounts. Thank you.